So good afternoon and welcome back to the second webinar of INSPYRE, the International School on Modern Physics and Research. In this webinar, we will talk about particle physics and accelerators together with Dr. Frederik van der Veken. Frederik is a researcher at the Beams department of CERN, and he has a PhD in theoretical particle physics. In particular, he studied the mathematical aspects of quantum chromodynamics. One of the research areas he's currently working on is the development of the machine learning techniques for beam dynamic studies at the CERN Large Hadron Collider. As usual, you can write your questions in the chat, and we will try to answer to some of them. So please, Frederik, the floor is yours.
Thank you. So, hi, everyone. I'm Frederik, as announced. Let's talk a bit about particle physics. So, in general, particle physics, we have big machines, high energies, tiny particles. These three fundamental concepts is physics at the femtoscale. So, first, very important question, what scale? We can say this a very fancy science word all the time, the buzzwords, femto this, femto that, but let's try to explain what it is. Well, a scale, we're talking sizes here, right? And you know, when I say particle physics, we zoom in quite a lot. So if we start for something we know in our daily life, standard matter, like a wood cube you can hold in your hand, we're talking about a few centimeters. So that's a 10 to the minus 2 meters. We zoom in, you could do more steps. We go to molecules or whatever. We zoom in quite a lot. We go to atoms. Typical size of an atom is what we call an angstrom, which is this cool A with a sphere on it. That's a 10 to the minus 10, so quite a zoom. An atom, as you know, is made of a nucleus and electrons around it. So we go to 0.01 picometers, which is 10 to the minus 14. And then the nucleus itself is made of protons and neutrons, which have the size of a femtometer, 10 to the minus 15, femtoscale. So that's why we call it femtoscale, because in these machines, we are typically colliding protons on each other, like we do, for example, in this big accelerator at CERN, where I'm working, the Large Hadron Accelerator, Large Hadron Collider. And of course, protons, maybe some of you know, protons and neutrons are made of quarks, which are then still 1,000 times smaller. We're talking atometers, 10 to the minus 18. Femto. Now, every scale needs specialized apparatus to be able to see it, right? For matter, like a wooden cube, we have a very highly technologically developed machine, RIs, very fancy materials there. Zooming in to atoms, we need microscopes. So to be fair, microscopes is more a bit bigger, a bit more molecules, but you get the idea. In the atoms, then we have electron microscopes, but then it's over. Then we cannot use simple tools that would fit in a room anymore. Then we go to big machines looking at protons, neutrons, and some ions, some nuclei. We need accelerators. This thingy here, you see I wrote in small letters, credit CERN. This was the first machine at CERN, the first accelerator, built in 1954, so that's quite a while ago. Synchrocyclotron. It's still here. It's not working, but people can visit it. It's first accelerator, and then of course we go deeper and deeper, higher energies. We need bigger machines. This is a photo/concept art, a bit between the two, because obviously our walls are not made of stars. Of the LHC underground tunnel, the 27-kilometer big machine, big. So the basic idea in particle physics is that we have big machines reaching high energy by accelerating protons, for example, here, protons which are of femtometer size, and we use them to search for tiny particles. As a general rule, you have seen the smaller we go in the scale we're looking at, the bigger the machine becomes. So this LHC thingy is 27 kilometers. That is quite big for a machine, I think you agree upon. So, step by step, let's look at the fundamental parts we have here to understand particle physics. Big machines was the first thing. All right, particle colliders. That's what we do. We collide particles, right? So how does it work? We accelerate particles. We have some protons. We accelerate them. We make them go faster. Now, to be fair, at a certain moment, acceleration here is more than just speed, because acceleration, as we feel it, of course, means we gain speed. We always go faster, faster, faster. But maybe some of you know, you cannot go faster than the speed of light. That's some kind of hard limit set by the laws of physics. You will not cross it. Meaning that the closer you get to the speed of light, the more difficult it becomes to go even faster. So we go exponentially closer. It's called asymptotically close in mathematical jargon. So in our case, that means our particles, they move at 99,99999, I don't know by heart, 69, I think, % of the speed of light. Very fast. So what do you do when you accelerate? You increase a lot the energy that the particle is carrying. And that's what we care about, because when they collide, this energy will be released. So that's the next step. We make them collide. We accelerate when we're happy with the amount of acceleration. In other words, when we're happy with the energy being carried by the particles that we're gonna collide, we're colliding them. So we smash them and release the extreme energy. Now, first thing here, already important to tell you, you might imagine that these very fast protons, the moment they smash, they collide, they break open and we see what's inside. But that's too simplistic of a view, because that is not what is happening. It is more subtle in the sense that the moment two protons collide, they're essentially gone. They're, well, a lot of people will tell you they're transformed into energy, the energy is released. All of these are just metaphors. What exactly is happening, we cannot say, because that's, quantum mechanics and their wizard thingy that happening there. But you could imagine that the energy that we put in these particles is now like made available by this collision, and we get some bowl of energy soup that we can then use some energy from to create a particle, create another particle, create another particle. And once the particle created, there is this leftover energy which we use to make them move. So all of this happens purely randomly. It's a purely random process. We have probabilities. I'll come back to that later. But typically, we collide, energy is released, made available, and particles appear. Of course, then particles appear. That's what we care about. We detect them. So we make these collisions happen at spots where we have detectors, well-tuned places, and we know there is a detector, and we observe the particles we see. And of course, we're looking for things we don't know yet, because it's a bit boring to keep on doing the same thing if you already know what it is. This is about discovery of new physics. So we look for signatures that would hint that we made actually new particles. And then, of course, you have this detection, but you have to understand what is happening. That is the whole point. So we analyze the results to deeply probe the mysteries of life, like I've written here, life with capital L, because, that's what it's all about, the laws of physics. So these are the steps we have in particle colliders: accelerate, collide, detect, understand. All of this is done in the collider by a machine, except the last part, that's humans. The machines are not yet completely ready to understand. Now, as I wrote, this is changing with the advent of machine learning, AI. They help us a lot understanding, because things become a bit unmanageable for our mere brains. But this is the general approach. Okay, so the best example we have of a particle collider is the Large Hadron Collider. Why is it the best example? Well, because it's large. It's our biggest example. It's 27 kilometers. I'll round it up, 26.659 kilometers. It has 9,593 magnets, almost 9,600 magnets. That's a lot. I think you can agree that's a lot of magnets. But then again, 27 kilometers is also quite big. So this is an aerial photo of the region with the collider drawn on top of it. It's around minus 100 meters deep, which is just mainly a, let's say, practical reason why we do that, because you see it crosses houses. People don't like it typically when you move them out of their house to make an accelerator, so we just go underground. It has added advantages while shielding of radiation, but that is not the main reason. The main reason is practicality. And we do quite a lot of collisions. We need data to understand. We need a lot of data. We need statistics. As I wrote, 1 to 2 billion collisions per second. We do that nonstop for hours. Machine is on day, night, nonstop for 9 months. Then we have a 3-month pause and we go again. So you can do the math in your head, between 1 and 2 billion collisions per second, nonstop for 9 months. That's a lot of collisions. So let's focus on the accelerating part. 9,000 something magnets, that's a lot. Now, maybe you've seen already, that's cool. Magnets, they have something like the Lorentz force, right? A charged particle moving in a magnetic field will be deviated. So you have the right-hand rule, force, magnetic field, electric current. So current would be the movement of a charged particle. So let's do that along the beam pipe. Then imagine that the magnet is vertical, the magnetic field. So this is, as for example, down there, south, north, or whatever, and then you get a force in that direction. Meaning a particle that moves like that, it will turn like that. Bending. Very cool stuff. However, that's not really helping us, right? Because, well, we want particles to accelerate. We want it to be pushing in the direction of movement. But now we're pushing to the left, but while the particle will be turning, well, this effect also turns. So it never accelerates. It just is going to make circles. So as I wrote, it's the wrong direction. It's like when you're swinging and you ask your brother, oh, please, can you help me? Can you push me a bit? And he starts pushing from the side. It's going to be fun. It's going to be a little chaotic, but it's not going to be faster. Fail. Magnets are not accelerators. That's a pity, though, because what? We have an electric field that works as a, let's say, exactly in the way we want it. So the force exercised by an electric field is longitudinal. That is a fancy word to say in the direction of movement. So if we have an electric particle moving in an electric field that is organized along its trajectory, it will get a push. We have for that what we call cavities, not cavities in teeth, but you know, a cavity just being a whole hollow thing. This is some brass alloy, whatever. It's quite big. It's something like that, and it's literally hollow. The fancy thing about it is the exact geometrical structure, the form, and then on this metal thing we put an electric field that will be switching. It's what we call an RF field, radio frequency, and we switch it all the time. To be correct, 400 million times per second the field is switched. All these things are big numbers, big machines, big numbers. 400 million times per second changing a field. Fancy, 400 megahertz. Why does that matter? Well, imagine in this exact drawing here of the cavity, you see the red beam coming in, red meaning positively charged, and then you see this field on this bubble in the cavity. On the left side is red, on the blue side, on the left side is red, on the right side is blue, red being positive, blue being negative. You can imagine, probably you have learned that before, like charges, they repel. So the protons, the positive beam coming in, will be slowed down a bit here. That's not what we want. So the field will be switched so that blue, which is negative, will attract plus, which is the beam, comes closer. The moment the beam is at that spot, it switches. So now it's going to push because now it's plus, plus, push, and switches again, push more. If you time that very nicely, after the cavity, it is a bit faster. Like correct time, you give it a small kick. Wrong timing, and your particle gets slowed down. So correct timing is very crucial. We have a few of these around the whole ring, and they actually will give our acceleration that we need. So we have the magnets, which were failed. We don't use them. We have the electric cavities, which is acceleration. Well, now I'm a bit contradicting myself, right? Because I said LHC has 9,600 magnets. So we don't use them. This is not true. Why do we use them then? Well, first of all, we're bending. Right, that's the whole point of a magnet. Bending, Lorentz force, right-hand rule, all these things. We're bending the particles around. Why does it matter? Well, we have a circle, right? Okay, it's not a perfect circle. We have some ring, 27 kilometers. Why would these particles stay inside? Imagine we have no magnets. Particles just go straight. And that is another thing, like we imagine, like the protons being a stream of water in a pipe, following the pipe. There is no reason why they would do that. They're highly energetic. They don't give a shit about your pipe. They're just going to leave the pipe and go straight. And then, well, then there is no way in using your accelerator because you lost the particles the moment you put them in. So the magnets actually are there to make them nicely inside the trajectory of the LHC. They make sure that they will stay inside. And then it is clearly like that the majority of the magnets in LHC let's say the space-wise, not number-wise, but the longest parts of magnetic fields in LHC are meant to bend the particles and keep them in a circle. Now, that's a dipole. We call that a dipole. A dipole is used for bending, exactly for the same reason as we had here, right? We have a vertical field and then a right-hand rule and blah, blah. We could make, well, you can see it, right? I have my mouse here. Let me show you. You see two coils like that. They typically will make a field which has north here, south here, or the opposite, so a vertical field. That's a bending magnet indeed. Well, we could make more coils, right? Why stop with 2? So you can see quadrupole, quad, 4, 1, 2, 3, 4. What does a quadrupole do? Well, you could imagine drawing the field lines would be a nice exercise, and then you could actually follow along the field lines with your right-hand rule and whatever. You would see that particles on the 2 extremities, so left and right, will be pushed towards each other. It's focusing. You're focusing the beam together, because that is a question I have avoided until now. Protons are all the same charge. Of course, in this machine, we're not putting one proton, accelerating it, colliding it. That's a waste of energy. Why? Well, we have 1 billion collisions per second, 1 to 2 billion collisions per second. We have a whole bunch of protons inside, and they stay inside for 10 hours on average, right? So, but they're all positively charged. Like charges, they fall apart. Remember, like charges, plus, plus, they repel. So your protons would just fall apart into pieces very fast. So that's why we have these quadrupoles, to put them back, focus them nicely. It is like a lens in a camera that will actually literally focus your particles. So a lens would do the same with light rays. It focuses them in a focal point. The only difference is that a magnetic lens, if you want to call it, so the quadrupole, can only focus in one direction. It will then defocus the other direction. So it will make let's say, a horizontal quadrupole will make a nice circle beam profile. We'll squeeze it like that horizontally and unsqueeze it vertically, so it becomes a pancake, flat pancake, which is why we always use 2 quadrupoles. They come in pairs, horizontal, vertical. So one does that, the other one does that. Just for information, then you might say, oh, but if you're first going to squeeze it like that and then squeeze it like that, the end result will be, again, the same circle. You are right. But that's the whole point, because otherwise they would fall apart. These quadrupoles, they make them into some kind of, you see, this stable oscillation thing. That's the whole point of the quadrupoles. And then we can go more, right? 6 sextupoles, octupoles. In the LHC, we have decapoles, 10, and dodecapoles, 12. These are for, as I wrote, other stuff, a lot of details. This is beam physics. I can tell you it is to keep everything even more stable, because we have so many things happening on a quite long time scale. Even the slightest distortion will actually make our beam fail. So we have these things to correct small. But for that reason, they don't have to be big. We have a lot of them, but they're quite small. These dipoles, they're 15 meters each. The quadrupoles, 5. And these higher order, they're in the order of half a meter or even a few centimeters, much smaller. So magnets do a lot of fancy stuff, mainly bending, other things. Electric field, the cavities, they accelerate. How does that look in practice? This is a schema, a drawing of the Large Hadron Collider. So this thing, 27 kilometer circumference. And you can see it is divided in 8 regions. Okay. Why is that? Because in every region, in the middle of each octant, as written there, something is happening. Something which is more than just bending. For example, we're colliding them. We're having an experiment. For example, we're accelerating them. And what other stuff. So the moment you're doing something, you don't have magnets. You have whatever you're doing. And that whatever you're doing means that there are no magnets, so this will be straight. So this will actually be, every octant has in the middle a straight part where we're doing stuff, and then the bend to the next octant. Straight part, bend to the next octant. The bends, by the way, they're quite long. I think, if I'm not mistaken, 2.7 kilometers per bend, so 8 bends. And then the straight parts will be 600 meters each. So we have 8 spots in the LHC where we can do something interesting. So what are they? So 4 are experiments. These are the nice stars. And actually you can see these lines, blue and red, that is the 2 beams. We have 2 opposing beams of protons. And there in these 4 stars, that's where the beams cross. That's where they collide. The other thing, we're doing stuff, but we're not colliding them. So blue typically is beam 1, red is beam 2. I think actually here the colors are switched. That doesn't really matter. It's a matter of convention. So we have 4 experiments. They are called CMS, Atlas, Alice, LHCb. So that's 4 times a big detector around a spot where we collide the beams. I will come back to that later. Then we have this octant 4. That is where we do the acceleration. RF and future experiment, or forget the future experiment, RF. So RF, radio frequency, acceleration. Now, you might imagine, wow, so this whole ring of 27 kilometers has only that spot for acceleration, only the 600 meter. That's not that much. It's even worse, because the 600 meter has a bunch of special magnets stabilizing the beam so it's ready to be accelerated, things like quadrupoles and other fancy stuff. The real acceleration is 33 meters. That's not a lot, right? 33 meters on 27 kilometers. Quite a lot of lost real estate, if you would think about it, right? You get 30 meters of acceleration and 27 kilometers of going back there. Now, yes, I would agree with you. But on the other hand, this thing is fast. I told you, particles move at the speed of light, almost, right? So that is almost 300,000 kilometers per second. That means that they make, per second, 11,000 turns, a bit more, 11,245 turns per second. So we get 11,000 times per second these 33 meters. So that would mean per second, you have 33 times 11, which is 363 kilometers of acceleration per second. I can tell you, acceleration in the LHC takes 20 minutes. Up to you, 363 kilometers per second for 20 minutes. That's a very, very big accelerator if you would make that in a line. So that is why we have always these ring designs. Even though the accelerating part is quite small, we pass so many times that it makes a lot of change. So you have these experiments 1, 2, 5, 8 octant. Octant 4 is RF, so the acceleration. We have 3 left, 3, 6, and 7. What do? 6 is dump. Dump is what it means, dump the beam. So to understand that, you have to understand the procedure of yeah, tell me.
Sorry to interrupt you. There is
No problem.
something not clear in one of the previous slides. They ask why all these magnets, dipoles, they come in pair. So
sorry.
always two.
Okay, so the magnets that come in pair is the quadrupoles. Maybe, sorry, I was a bit too fast on that detail. So the dipoles don't come in pairs. They just come in whatever number we need. The quadrupoles, as I told you, they do focusing.
No, I guess, sorry to interrupt, I guess you see always 2. Why there are 2?
2 beams. Sorry. Okay, very good question. This is the 2 beams. Yeah, so you can imagine here there is a beam of protons going in that direction, and here there is a beam of protons coming out. You can see my mouse, right? The red dot.
Right. Yes.
Okay, so that is representing the 2 beams. And also this thing, even though you have some rounding around it, you can see there is a big circle metal yoke around it. So the magnets are just single things, single magnets, but inside, of course, you have the 2 beams. They're pretty close. Huh? We're literally talking about this. That would be the real size. So that's, 10 centimeters apart? Does that answer the question?
Absolutely, yes. Thank you very much.
If not, interrupt me again. All right, so we were at the beam dump. For the beam dump, you have to understand a bit how this procedure works, right? Because we always say proton on proton, bang, and we have what we want. I already hinted in the beginning, it's slightly more complicated. We have 1 to 2 billion collisions per second. You're not gonna accelerate a proton from 0 to that 1 billion times per second. That's impossible. So we work in beams, in bunches, and whatever. We start with a whole bunch of protons. So I will show you in a bit later. It goes in stages. So the moment our protons come in the LHC, they're already at a certain energy. But then we need to accelerate them. So first we fill them until the LHC is full with protons at this energy. And then, okay, now we start. That takes, depending on the quality, 20 to 40 minutes. Then we say, okay, we start acceleration. We start building up the energy. We call that ramping up the energy. So accelerating, viewing until we're happy, another 20 minutes, a bit more. And then we're, okay, now we start collisions. And we start colliding them at the different experiments. Now, every time two protons collide, well, they're gone. As I said, you get this soup of energy, particles are created. So we have less protons left in the beam to collide. To give you an idea of scale, our beam is around 10 to the 14 protons. So what would that mean in normal language? 100,000 billion, right? Yes, 100,000 billion protons. Sounds like a lot, it's not. 10 to the 14 in a drop of water, you have 10 to the 24 protons in one drop of water. So this is much less than a drop of water. On the other hand, it sounds more than enough to make these collisions, right? Well, kinda, because we get 2 billion collisions per second. So that means, well, in most of the collisions happen actually in CMS and Atlas, in the two big ones. So that is 4 billion collisions per second, and each collision burns 2 protons. So we're losing 8 billion protons per second. Let's say, let's round up a bit, 10 billion protons per second are gone. So 10 billion is 10 to the 10. We have 10 to the 14, so every second we lose 10 to the 10. That's a lot. So you can imagine that the number of collisions goes down, because the more are gone, the less is left to collide, and the chance of collision goes down. So the number of collisions, can imagine, goes down over time exponentially like that. And at some point, we decide like, okay, yeah, the rate is too low. We don't get enough collisions anymore. We restart, because we're not going to wait until it's 0. That's going to take ages. The less you have, the slower, of course, it goes down, because the less you have, the less collisions you have, so the less you lose. So we're not going to wait until infinity. At some point, we decide, yeah, let's start over with a fresh fill, we call that. So we start over with filling it, ramping it, and everything. But then you have this leftover, which you need to, well, get rid of. Let's dump. We dump them. It's a block concrete and some tungsten and whatever nice stuff that can handle it. I don't know the exact size. I think it's 10 meter long, 1 by 1 meter, something like that, a bit small, well, probably a bit smaller. And then you're just sending the beam in there, the leftover beam, and then it's empty, it's clean, you start over again. And we do that non-stop, day and night. So on average, we can say we have 2 hours of preparation, so injection, preparation, ramping the energy, acceleration, until we start colliding, which we then do on average a bit less than 10 hours before we dump. This can be different because it's a bit random on how qualitative, let's say, our beam is. Like the maximum we've had the beam the last 2 years was 42 hours for one fill. That's quite a lot. The minimum is, well, 1 second. We start, you're like, oh, this beam is shit. You dump it and you start over. Luckily, that doesn't happen all the time. But so there is a whole spread, an average of 10 hours. That's why dump is important. And then the last 2, 3 and 7, they have a similar function, which is beam cleaning. These are collimators. What does that mean? Well, these protons, I told you, like charges repel. So they like to fall apart. We have this whole thing with the quadrupoles to get them in stable oscillation in some kind of orbit. Fine, that works, but it's never perfect. Nothing is perfect in the world. Neither is our machine. However, here we care. These protons that are not perfect, let's say, they start falling out. Not so much. So we don't care about losing the intensity of the beam. We don't care about, oh, we don't have enough collisions. This is not the point. The point is that they're highly energetic, these protons, and they enter up in the magnets. That is a problem, because these magnets need to be enormously strong. These are the strongest magnets in the world that are used in production. 8 Tesla, if you know what a Tesla is, it's very, very strong. To achieve that, they are superconductive, meaning that they have been cooled, or they are being cooled to extremely low temperatures. You know, there is an absolute 0 Kelvin. You cannot go below that. Special materials like superconductors, when you get close to that, they suddenly lose all resistance and they become perfect, meaning that you can put a lot of electric current through something with actually that not be able to handle it. You know current, ampere, the electric current. You've heard of that, and you know that if you have something which has a lot of ampere, the cable needs to be thicker. like a washing machine draws 16 ampere. That's a strong machine. 16 ampere, you need a cable which has 1.5 centimeter squared. I'm not sure, I'm not a specialist, but I think it's kind of that. While if you're talking about a current of a few milliamperes, you can do it through very thin wires. That is because even though the copper wire is a conductor, it still has some small resistance. The current we use in our magnets is a totally different story. To give you an idea about size, 50 milliamperes kills a human. The maximum that a household can deliver, the fuse box, let's say, will burn if you go over it, is 32 amperes. So you can put 2 washing machines at the same time, but then you're not protected against potential peaks, which is why people advise against that. 32 amperes will blow the fuse if you go over it. That's a lot of current. While our magnet, one magnet takes 13,000 amperes. A lot of current. You would need a copper cable, which has this size, like, what is that? I don't know, 10 centimeter radius more. We have them above ground where we deliver the current down. It goes in these things. But then when it arrives, the current to the magnet, it goes superconductive. And the wires become the width of a hair. I have a lot of hair, but luckily it's not used for a superconductor. But that's how it looks like. You're sending 13,000 amperes through this small wire because it's superconductor. You can make it very tiny wound, and you have a perfect machine. Now, all nice and happy until these protons that are falling out hit your superconductive magnets. Because what does it do? It will heat it up. It heats up. It loses its cooling. It goes a bit above this threshold. It's no longer superconductive, and it explodes. I mean, not explodes, but it's broken for sure. We call that quenching. So we don't want that. So we have collimators at these 2 places, 3 and 7, to clean the beam. It's literally plates like that. I mean, like jaws, they're quite long, 1 meter typically, of dense material. Tungsten, tungsten wolfram, you know, that's a very dense material. You put them very close, like a few millimeters. This is the beam pipe, right? So that is 5 centimeters, a bit less. And then you put these things very close around the beam so that protons that are already falling out slightly will be intercepted by these collimators. That is to protect the magnets. Very important part. We would not be able to reach these energies if you could not protect the magnets. So here we have it. 8 spots where something is happening in the LHC, of which 4 experiments. Beam cleaning, that's 3 and 7. Acceleration, that's 4. And dump, that is 6. I told you we go in stages. This is just to give you a bit of flavor. We don't start with the beam directly in the LHC. The magnets have to adapt for the energy, and they don't have that flexibility to adapt from 0 to their maximum. So we started actually here, LINAC 2, from some gas bottle. And that's a linear accelerator of some 30 meters, so just... And then we start with a smaller circle, 157 meters. Bigger, 628. Then we go here, whoopla, SPS, 7 kilometers. That's already underground. And then we split 2 of them in 2 beams. This one goes to beam 2. This one becomes beam 1. And then they start going in the big accelerator LHC. So the energy they have here is some, what would it be? Some 20th. So the final energy divided by 20. So the magnets do not have to change that much. And that's exactly what I want. That's why we have all these stages. And so, of course, because these rings are smaller, you cannot put all the protons that would fill the complete LHC in this tiny thing. It goes in stages. This thing will do a few times to fill that one. Well, it has actually four rings on top stacked, so it can do it in one go. This thing will do a few of it to fill that one, which will do a few of it to fill that one, which is why it takes 20 minutes to fill. And then we start the acceleration. All right, so maybe something quick about the detectors. Detectors are big. Our machine is big, everything is big. So this is CMS. You see, this is a human. I mean, not a real human, it's a drawing, but it's up to size. And here, this tiny thing in the middle, that is the innermost part of the detector. That's where they collide. We can decide exactly the point where they collide. So at that point, we make, where the beams cross, right? So at that point, we make our detector, which is some 15-meter diameter like that, and some 30 meters long. That's CMS. Atlas, which is the 2 main experiments, Atlas, CMS. Atlas is slightly bigger, I think 25-meter diameter and up to 40 or maybe even 50 meters long. The reason Atlas is bigger is not because it's cooler or has more, it's just because they're not, they organized everything different. There is more air in between. C for in CMS, so CMS detector, C is compact. Everything is made compact, squeezed together. Each design has its advantages, its pros and cons. What is every detector based on? An onion-like structure. You have layers, and every layer depends a different way to recognize particles. You're recognizing their energy, their charge, these kind of things. They're sometimes a bit their type or their family at least. So that is why detectors have this layer-like structure. And that is what you can see it very clearly. We have the innermost, you see the two yellow discs, and there is a very small one here. So that's the pixel detector, which is kind of this size. I think diameter, something like that. And then we have another layer, which is this blue one. Then we have another layer, the green one, the yellow one. This white thing is the magnet. Then, and we have here, the red things are just frame. It's a return yoke. The white things here, that is muon chambers. That's also detection. So you have this onion-like structure for different types of detectors. All detectors, they have that. That is the, let's say, standard way in particle physics to recognize things. You need different layers of different way of detecting, which makes them quite big. It also makes them, like, it limits a bit what you can do. Because if you're like, oh, I want to add some other way of detecting some extra layer, well, it gets big in the end, right? You want to add a layer to this, it has to be all around, so it gets a very big layer. So that's for colliders typically the case. You can have also detectors that go actually in one direction only, so which is very typical for fixed target experiments, where you have not two beams colliding, but one target which is stationary, and then a beam that hits it. Then whatever is created will be smashed in that direction. And so you just put layers, slices. That's much easier to make. There are disadvantages to this setup, but as usual, always pro and cons. Typical experiments are like that, with the exception of LSCB, which has a bit this setup.
I'm here again, Frederik.
Tell me.
Sorry, but this concept, they are a bit later, so there is a bit of delay in questions. So it's not clear how these particles are traveling inside the beam pipe, if all together or if they're bunched.
Okay, so there are bunches. You hinted. The bunches, they come from two facts. First of all, this let's say the main reason for bunches is that we have this acceleration, right? So if you would have a continuous stream of particles coming in, remember this cavity, it is flipping the electromagnetic field. So if you have a continuous stream, there is always a part that is wrong, that will be slowed down actually, and there is a part that is right, that will be accelerated. So that's why you put them in packages to get the correct kick every time of acceleration. Now, why is this a natural consequence? Because in the initial stages here, where you have the whole similar design of acceleration, those that are wrong, they will be slowed down and they end up anyway in the correct position afterwards. So you end up in a system that is bunched. So a package of particles, nothing. Package of particles, nothing. Package of particles, nothing. And then the whole machine is filled like that. In the LHC, we have some 2,000 something bunches. To give you an idea of scale, they're typically 1 millimeter diameter. And let's say most particles are within 7 centimeters, but they can go up to 30 something centimeters. And that would be one bunch, with the majority being within 7 centimeters in the middle. And then you have, in the LHC at least, 9 times the size, nothing. And then you have another bunch. So they're quite far apart, which we do on purpose to avoid them influencing each other. And then you have, between these bunches, you have some major openings, what we call gaps, which is whenever you inject something, for example, from PS to SPS, you do a whole set of bunches, but then you're breathing, right? Then now PS here is having new ones ready while these ones are waiting. Then you need to time it nicely. And the problem is there are magnets here that will push them in. These magnets need a bit of time before they reach their full energy, before they can do that. So you need to leave some gap before you can do a next, what we call train of bunches. So inside the LHC, particles will be in packages together, mainly nicely spaced, with every now and then some bigger gap. Just very good question. Sorry?
Thank you very much.
Okay, perfect. Good. So very good question. Important to ask this kind of question. So for all the others, feel free to every time interrupt me, ask me. So I was talking about these onion-like layers of the experiment. So here, that's another thing, because we have these bunches, we can decide exactly when they cross and how they collide. We can tune all these things. And then per crossing, you have a crossing of, let's say, a bunch here, a bunch there, they cross. We cannot say, hit that proton, impossible. No, we just make them as dense as possible. We squeeze them. So at the moment of crossing, they're 1 micrometer instead of 1 millimeter. They're very, very tiny, squeezed. And then we cross them. We just hope that some will collide. That's probability. And actually, with this squeeze and this number of protons in one bunch, around 60 collisions will happen in one crossing. And that's how it works. Yeah, I found, and then this was actually 60 collisions. And then it's up to the particle physicists when they made their snapshot, because in the moment of crossing, you make a snapshot of the detector to distinguish which particle belongs to which of the 60 collisions. These are averages, sometimes more, sometimes less, but that's a bit the idea. Let's forget that and let's single out one collision. This would be some angular slice of the detector. So you can imagine I'm just cutting out a slice like that, something like that, right? That would look like this, and you see the different materials. We have this inner part, the green, white, yellow, magnet, and then here the red, I told you, was a return yoke. It just means it's a frame, it's metal, helps to stabilize the magnetic field. And in between here, were these white things, the muon chambers. So how it works in these different layers is that not all particles will be able to go all the way through. There will be particles that are stopped already at the first, what we call calorimeter, which is a dense material absorbing them. So the lighter particles, they will stop there, and lower energetic ones as well. Then after that, the yellow one, we have a hadron calorimeter, which will take the heavy particles out. So at the end of the yellow one, which is just inside the magnet, almost all particles are already out. There is one that can go still through because of how the way it's generated. That's physics makes that these particles will go through. That's muons. That's this blue line. So that's why these things are called muon detectors, because if they see something, it's a muon. Now, there are more particles than that. Like this thing here is a tracker. It will show us the tracks. Magnet is added to make the particles bend depending on the charge. So then we can see, oh, it bends that way, positive, bends this way, negative. That's already nice. It doesn't bend, neutral, no charge. So neutral, no charge, doesn't bend, but also in this tracker thing, what we call tracker that shows our tracks, it will not have a track because neutral particles don't interact with this machinery, so you get no track. Now, neutral particles, they still deposit, meaning that they still enter or slow down. So we will see that. And how do we see that? Well, this material is absorbing these particles, right? Well, absorbing means where did the energy go? You heat up the material, for example, and then you measure the temperature difference, and something was here with this amount of energy. This can be done by literally temperature. This can be done what's typically done here by light. We have a crystal light thingy. Particles go in, they will start radiating light, and you just measure the light. The intensity of the light will be equal to the energy of the original particle. So then we can start seeing, okay, something, no track here, some deposit here means neutral. So the dashed line we don't see, right? But we can easily make that line because we know they were not bent. So light, not heavy, no charge, photon. Exactly, photon. Nice. Then this one, positive, bending down, right? Going through this light calorimeter, but still going through, so not absorbed. So heavy particle stopping here, heavy particle stopping here, positive. Proton, for example, proton. This red line bending the other way, so negative, stopping here, not going through, so not heavy, negative, electron. Dash line here, no track, deposit in the end, so heavy, no charge, neutron. And then, as I said, whenever it makes a signal here, muon. To be clear, there are more particles that can go out, like neutrinos. Neutrinos we don't see anyway, so they don't give a signal. We need some physics to deduce where they were. So this is why we have the layer system, because it helps us decide what was happening. Good. This was the setup of the machines. Let's go now to what we're doing. Tiny particles. So why do we do this, right? Why build a machine that is 27 kilometers big, costs 7 billion euros? That's a lot of money, I think you agree. Why? Because we want to answer fundamental questions. That's the point of fundamental science. We're not looking for direct applications. We're not looking for new machines or new technology. No. We're answering fundamental questions. You cannot progress in science. You cannot progress in technology if you don't answer fundamental questions. That's always the first step. Fundamental questions like, what are we made of? What is the universe made of? We are not the same as the universe. It works maybe different, maybe the same. Why do things work? Like that seems like a ridiculous question, but that's a very, very fundamental question. Why are we standing on Earth and not floating up? Gravity, right? But these are very important questions. Things that seem the most trivial are typically the most deep and most difficult to explain. And whatever other question you can think of, fundamental questions. Right, so let's see a bit history of particle physics. This is one of my absolute favorite plots. I will tell you why. It's called Basic Bricks of the Universe. What is it showing? On the horizontal axis, time. Time, it's not linear. You see 1000 BC before Christ, so minus 1000. 0 is the year of Christ. 1000, then we go to medieval times. Then we go to the Enlightenment, 1800, 1900s, 1950, 1980, 2020, 2020. So that's progression over time. What is on the vertical axis? The number of particles that humans believed are the fundamental bricks. Let me rephrase that. The number of particles that humans believed are the fundamental bricks. There was a moment where people believed that everything was built of 4. Fire, air, water, earth. Eratosthenes, that's this guy, the nature philosophers of ancient Greece. There is even another one, which was not in the plot, Democritus, who said everything is not from one thing. So then actually the plot would go even a bit deeper, because you see here, 1, 2, 3, 4, right? This moment in time, I think it's minus 500 something, the nature philosophies, people believed everything was built of 4 basic bricks. So around that time as well, there is a dip to 1 by Democritus, who said everything should be made of things that are indivisible, not divisible in other things, so like basic brick, and which is in Greek atomos. Tomos means slicing, dividing, which is also tomography, for example. So atomos would mean not divisible. An atom, that's where the name atom comes from. Thank you, Democritus. So the plot is missing this dip to 1 for Democritus, but you get the gist, right? 4, Democritus was not so famous in his time anyway, so people won't be mad if you forget him in the plot. And now we go to medieval times. The alchemists who said, we have a set of elemental fundamental particles, and even you can transform them. Well, they were wrong there, right? Things like gold, bismuth, antimony, phosphorus, lead, they were quite right about their fundamental thing there, because these are the elements as we know them, some of them. They were wrong that you could think you can change one and the other, so which is why lead and gold, they were looking for the way to make lead into gold and stuff. That is much more, let's say, well, untrivial at least. And then 1800s, we have this guy with the big beard, Mendeleev, who discovers that actually all these elements can be categorized. And that was a big thing, because that means that you can categorize them in function of similar properties and similar behavior. We like categorizing in physics, because if you categorize, you can understand what is happening there. There is some tendency, some structures, and all these things. So he discovered that, for example, this column of elements would behave similar, and this column would behave kind of similar. We know now that, of course, the different columns mean different amount of free electrons on the outer orbit. So we understand now, but we didn't in the beginning. That's why categorizing is so important. You see, you can sort them by property, and that actually helps you understand what might cause that property, which, again, I said these electrons, but he didn't know that. So, table of Mendeleev. Wow, we came from 4, 1, if we include Democritus, fundamental bricks to, well, at Mendeleev's time, we stopped where? I think uranium, somewhere there. Probably, that's the latest, biggest stable element. So 92. We go from 1 to 92 fundamental bricks of the universe. That's a lot. I think you agree. So that would be somewhere here by that time the elements were discovered. And then you have some people that are discovering, what? Every atom has a nucleus that has protons and electrons. Bam, 2. That's a big jump down. I think you agree, right? I forgot to mention, of course, before the nature philosophers, this was unlimited. People did not ask the question. Wood was fundamental. Water was fundamental. Air was fundamental. Salt was fundamental. There would be an infinite amount of basic elements in the universe, right? So they were the first one to categorize it. So that's why I have a big fall down here, because you come from as many as there exist to some number. And that's what I like about this plot, this falling down and growing again, falling down and growing again. So we fell down to 4, but then we go back to, no, 92. We fell down to 2 protons because neutrons were not yet discovered. This is Rutherford and Bohr. 2 fundamental bricks. Wow, that's much better than 92. And then we go up again because then we start discovering, oh, there's also a neutron. Oh, there's also a positron. Oh, there is also a neutron. Oh, I said neutron, right? There's a whole bunch of muons that were discovered. Then they start discovering these variants, like special mesons, pions, kaons, and whatever, a whole zoo of particles, and we're getting close to 100 again. And then you have this guy, Gell-Mann. Gell-Mann, who discovers, again, you can categorize them. Categorization is always the key to say that there are fundamental properties. This categorization led to the understanding that actually it is just protons and electrons, right? This categorization, which is called the eightfolded way, because you see 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and a bit more. Well, generally, it's called eightfold way because not because it's always 8, but just because that's a theme from Buddhism. The eightfold way is the 8 things you should live your life to be to become the Buddha. So that is also nice to call it like that. This one is 8, this one is 8, and this one is a bit more. Anyway, the categorization here was the first hint that these things, like proton, neutron, these pions, and all these things, are not fundamental. They're again built from somebody else, something else, not somebody, something else, quarks. And we fall down again. A twink. Well, now we have a bit more. We're not to 2, right? We have some quarks, we have electrons, we have muons, so a bit more than 2 at least. And then it starts going up again because now we start discovering, oh, but there are more than 3 quarks. In the beginning, they thought there were 3 quarks. Now we know there's 6. And then we discover we discover, there's except the electron, muon, we also have a tau. Things go up again, tick, 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 tick. And the last step here was the Higgs boson. Oh, sorry, here, actually, before, when we start discovering all these things, there are these 3 people, Glasshouse, Salam, Weinberg, who were able to, again, categorize them, which is called the standard model, 16 particles. And then in the last step here, this last kink, that was the Higgs boson. Braud, this guy, Angler, and Higgs, they predicted the field. Only this guy predicted the boson, the particle, so he gets to name the particle. Fundamental particles, 17. Tell me.
Previous slide, so they ask why the curve starts at 100.
So it doesn't start at 100, it starts at infinite. That's what I said. Before anybody actually asking the question, what are we made of, people just assumed that everything was its own element. Lead being lead, water being water, wood being wood, and that it was not built of something, right? And we underestimate the importance of these very simple questions. Like here, the very simple question, are these things fundamental or is it built of something? The first ones asking that were these Greek philosophers. So they came up with everything is built of special combinations of air, fire, water, and earth, which we now, well, no, this is not right, obviously, but that is their way of saying, okay, there are just combinations. So that's where it goes to 4. But before them, this question was not even asked. So how many elements? Well, as many as you know, right? And then you ask different people, you get a different answer. So that's why it's infinite. Whatever element that people would know that exists.
Okay, thank you.
I hope that was an understandable explanation at least. But so 17, we come 17. That's what we today believe is the number of fundamental particles. More than 1, more than 2, but still less than infinite, right? So that's what we believe fundamental particles. 17, these 17. We have some quarks, 6 of them. We have some leptons, 6 of them. So electron, muon, tau, and then neutrinos. We have 4 force carriers, gluon, photon, boson, the Z boson, W boson, and the Higgs boson. No gravity, because we don't know how to get gravity yet. We don't know yet how to get gravity in this quantum mechanics. Then you can say, oh, but there are also antiparticles, positron, muon. Yes, but we consider that the symmetry. We consider a positron just some kind of mirrored electron. So we don't count it as a fundamental particle. 17 fundamental particles. All right. Last chapter, high energy, big machines, tiny particles, high energy. So, if you don't know this guy that makes this kind of comics, it's XKCD. These are the best nerd comics ever. And here he explains the 4 fundamental forces we have in nature, in the universe. We have gravity, electromagnetism, strong nuclear force, and the weak force. And one by one, he starts explaining them. So gravity is an easy one to explain. We have what we call the inverse square law. So if you have two mass, m1, m2, on a distance d, the force of attraction between those will be some constant g, Newton's constant, times mass 1 times mass 2 divided by the distance squared. That's gravity, easy to explain. 2, electromagnetism, very similar. Two charges, q1, q2, with some constant in front, will have a force attractive or repulsive with 1 over the distance squared. Very similar, except, and that's why it's in a bit small print, Maxwell's equation. Maxwell's equation, they allow for electromagnetic waves to exist. It complicates the matter a lot, because then, well, there are few formulas. It's much less nice than that one to show. So also that's hiding a bit of difficulty. Then we go to the strong nuclear force, for which we don't have a law like that. We don't have it. You cannot use that because it's behaving in very strange ways. As I said, this is actually what I did my PhD on. It is funky, is a good way to say it, because it works opposite. The closer they are, the weaker they interact. Now, with this electromagnetic and gravity, it's the opposite, right? If you have two magnets, for example, the closer they are, snap. The closer, the stronger the force. That makes a lot of sense. That's the 1 over d squared. Because if d becomes small, its inverse becomes big. So the force becomes stronger, stronger, stronger. This thing, no. The more you separate them, the more it will pull back. So that's as if it goes with the distance, right? The difference is only that there is a distance which you cannot cross. You cannot go farther. If you still try, you will break the force. You can imagine that this is like a rubber band, right? If it's close, the rubber band, there is no tension, there's no force. But then you start pulling more and more, it will pull back. And then until you over-force it and the band snaps. You do this here. You get a quark and an antiquark, for example, which are nicely bound together. They're very happy minding their business, not having any force. You start separating them. They'll be like, nope, 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 nope. You insist you separate. The moment the band snaps is when in the middle, suddenly two new quarks are created out of the blue. And you get two pairs. Impossible to separate a quark. Impossible. You will never separate a quark. So you don't have a formula to describe that behavior, right? So that's the What does it do? Well, it holds protons and neutrons together in the nucleus, because why would they stay together? The same charge protons, they would repel. Strong force keeps them together, keeps quarks in the proton together. And the last one, the weak force, even more complicated to explain, because that is actually particles changing in other particles. That's not just some force law. No, that is one particle going in another. And that is actually what creates radioactive decay and all kinds of radioactivity. So these are the four fundamental forces, getting from easiest to explain to most difficult to explain. And then the thing is, what is the one we don't understand? This one, gravity. This one, we don't understand how this fits in our existing models, which is one of the biggest open questions we have in science at this moment. I like this way of explaining it. So I see we're getting quite a lot of time used already. So let me show quickly one more thing, which I think is pretty cool. How does it work? How can we, when we collide two protons, from that deduce that we made the Higgs? And for example, that the Brout-Englert-Higgs theory is right, because that's the point, right? These three guys, they made a theory in the 60s, and we want to show them right. And then we needed until 2012, which is 50 years later, to say, oh yeah, actually, you're right. So first of all, that's why we needed so many collisions, such high energy and blah, blah, blah. But how do we do it? The problem with these things is if you go to such high energy, they become incredibly unstable. Higgs boson is so unstable that it decays before you can measure it. It decays in the order of even less than femtometers. You are not going to see that resolution in your machine. So whenever somebody tells you, we found the Higgs, we've seen it, you can tell them, that is an abuse of words, just to make things explain them easily. There is not one collision where you can say, this was a Higgs. Impossible. It's statistics. And I will explain you how that works. It's the black box mechanism. We know what we put in. Two protons. We measure what comes out, a whole bunch of shizzle. That's our detector checking at these things. We don't know what happened in between. It's a black box because we cannot measure it. It's too small. So we use statistics to deduce, we make predictions, and we see what it will happen. What does it mean in practice? In practice means that this is, of course, what we're interested in. So let's see how that works. Statistics. Statistics is cool, huh? This is the plot that showed the world, this is the Atlas plot, that we found the Higgs. When this plot was shown on the big screen in the main hall at CERN, everybody stood up and gave a standing ovation, applauding. This plot proves that the Higgs is found. That's statistics. That's the power of statistics. What does that mean? That means that we are plotting some information. So we're looking at something very specific, which is in this chisel, of particles generated here, we have 2 photons. It's a condition for that plot. Well, you can look at other stuff, but this one is looking at 2 photons. So we see, okay, we have a bunch of things, and let's say a bunch of things in, you collide like that, a bunch of things here, but then very clearly transversally, so perpendicular, 2 photons. Okay, that's our situation. Now we're going to measure the energy of these 2 photons, and we prove that here. Okay. Now, our theory, the whole theory without the Higgs, which has been proven in different experiments over the last 100 years, tells us that how many times something should happen statistically, right? At this energy, it goes down exponentially like that with energy. So you would see more what we call events, so more times these 2 photons at a lower energy than at a higher energy. So that is this dashed line here. That is what we call background. That is what we know how it looks like. If there is a Higgs around the mass of the Higgs here, so 125, it would happen more. We don't know this mass of the Higgs. Now we know, but we didn't know in advance, so you have to scan, right? But then you would see more happening there. Here, plop. That's this small bubble. That means that there is something here. Now, before you can say that, of course, you need accuracy. And that's where statistic comes in. Like, if you throw a die, what's the average? I can tell you the average is 3.5. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. 3.5. That's the average of a die. I think you will agree with me. If you roll it once, you're not going to roll the average. Right? You can roll 6, you can roll 3, but you're not going to roll 3.5. If you roll it 10 times and you take the average of the 10 rolls, yeah, it might be 3.5, but it might be also 4. You might have a lot of high rolls. You get 5 as an average, right? It's not going to be 3.5. But I think you agree, when you did 1,000 times, it's going to be pretty close to 3.5. If you roll a die 1,000,000 times, you're going to have 3.4999 or 3.500001. It's going to be very close to 3.5. And that's what we're doing here. If you would have only one in that direction, it's meaningless. It can be noise. It's not accuracy. But if you have a lot of them and they nicely follow this curve, then you have proven your point. Now, while I'm saying it, I realize that this seems so much like an overstatement because that's not what they're doing. Like, look here below, here above, bang, bang, boom, bang, bang. I would not, I mean, this is wishful thinking that from this line you have nothing here and then suddenly a bulb here. I would make the line like that, exactly. I fully agree with you. The point is that what this plot is showing is a sum of a lot of other things which are not inside. And then we can calculate with statistics, with some mathematics formula, what is the chance that this thing here is literally just a fluctuation like this here? And what is the chance that it's actually a signal? And so if you combine all these different plots, you will see that this one's actually, another case are like that, like that, like that. So they average out to 0. But this one remains stably present. And then we use our statistics or mathematical formulas to give it a number. If the chance that this is just noise is less than 1 over 139 million, that's a small chance. Then we call it, we found the particle. We call that the 5 sigma threshold. And obviously we did, right? That was why it was found. We had so many, and that's why you need so many data. That's why you need 2 billion collisions per second to get this 1 million throw on a dice that you have a 3.5 with accuracy. We cannot steer. We cannot say every time you get a Higgs. No, most of them not produce a Higgs. So you need more and more and more and more. 2 billion times per second times all the seconds of 2 years of data taking, and that's it. Example process, 2 protons coming in, protons radiating each a gluon, and then being destroyed. Some shizzle happening here, we don't care. The gluon then makes what we call a top loop. These are quarks. Becomes a Higgs. Before we can measure the Higgs, it's gone again and becomes 2 photons. That is the black box. That is the part we cannot measure. We see 2 protons in, shizzle out, and 2 photons out. We use the probability with what we know that we expect and what extra we see to deduce we found something. And then, okay, that is step one. You found a particle here, tac, tac, at the mass 125. So this is when people get the applause, but this is not when people got the Nobel Prize. This is when people got the Nobel Prize, because here you prove that particle that we just found is actually behaving what we expect to be a Higgs. What does the Higgs do? You have heard it maybe. It gives mass to particles. That's again an oversimplification. We like oversimplification because otherwise these talks take 5 weeks. But that's the idea. It gives mass. Somehow we would see that it happens more with heavier particles. That's the baseline. And then you see how many times it happens, goes up when the particles are more heavy. This is the data. If it would not be the Higgs, it would do some random thing like that. But it does. These are the measurements. 1, 2, 3, 4, 5. They're perfect on the line. This plot gave the Nobel Prize. And then how do we calculate these probabilities? As I say, we know it will be exponential, these things. That's what Feynman diagram says for. So it looks like that. You have arrow lines to say fermions, so matter particles, quarks, leptons, and then wavy lines, coiled lines, wavy lines for all the forces. And then you start making, it's puzzling. You make all these diagrams, you puzzle. And then for every diagram, for everything you see here, we have a mathematical analogy. And then when you combine it, you know, okay, that is this formula. And then you combine them in every way possible. And then you sum all these possible formulas. It's a lot of work. And then you get your probability. All right. I guess I can maybe skip this one. It's over time. I don't know. I'm asking the moderators here. What if nobody's intervening? Pascal.
Well, let's say it was a bit long as a talk, but you can conclude for sure. You can.
Okay, sure. So this one is just, we want a bigger machine, right? We always want the biggest. That's very human. So we want a 100-kilometer machine. This is LHC, and then the LHC would be used as a 4-step of the big one. So this was a 27. This is 100-kilometer. I live here. Ta-da! So big machine. It's planned. Approved in design, not approved in money, because this thing will be very expensive. Let's see, it would be for 2040. And then, okay, there are some theoretical open questions. That will be for another time. One more thing that's maybe a nice one. On this plot, we have this hope for everything is reduced to one particle, right? We always like that. One is so much nicer than 17. So can we find a fundamental particle that is one and that makes everything? Can that be string theory? That's one of the big theories. String theory is saying that everything is one string, one like a musical string, but very small, and then the frequency defines what it will be and what it will behave like. It can, but I say nah. Me and I would say a lot of physicists at this time start believing that even though it's a very nice theory, it's very nicely built. I did my master's in string theory, by the way. It is getting a bit unlikely. We would have expected some signals, and it does not mean that it doesn't work. You can always make it work. You can make every theory work. You can add stuff to make your theory work. But once you need to fiddle to make your theory work, people start losing faith in it, because nature is not like that. Nature doesn't fiddle. Nature is like for the easiest thing possible. There was a philosopher in the medieval time, Occam, and he has a philosophy that is called Occam's razor. And it's basically boils down to, if you have several ways to explain something, the easiest one will be the correct one. That is true. I mean, true. It is not an absolute truth, but up to today, this has always been true. The Higgs theory is very complicated, but was the easiest way to do it. Like, the problem with string theory is there is no other way at this moment, right? But there were easy versions of string theory, and they have been ruled out in the last 5 years. So it becomes quite complicated, and that's why people start saying, maybe not, maybe not. A lot of open questions for people like you when you step into the world of science and can be our new Nobel Prize winners. But mainly thanks for your attention. If you have questions, I don't know if we still have time now. Otherwise, feel always free to send me an email. I will reply. Mostly of the time, I'm a bit chaotic. I will try to reply soon and fast. Feel free to ask again if I don't reply. Thank you.
Thank you, Frederik. This was a fantastic overview of particle physics and status. let's take a couple of minutes to answer two urgent questions. So one was, in the beginning of your talk, you showed that by accelerator we probe quarks whose dimensions are 10 to the minus 18 meters. Is this the shortest dimension or the smallest dimension that we can probe?
I would say at that level, dimension becomes a bit meaningless, because anyway, we're not seeing them, right? It's in the same story as before. We don't see atometers. We don't have that kind of resolution. What it means is that you could calculate from a certain interaction at what distance they start to interact. So that's what we call the size. But even, for example, the size of the proton, 10 to the minus 15 meters, 1 femtometer, even that is actually something which is, well, it is not a marble, right? A proton is not a marble of that size. A proton is also not a combination of 3 marbles that behave like 1 marble. No. It is, well, whatever quantum state that you can imagine. It's difficult to give that sizes. What this 1 femtometer means is that when a photon tries to go closer than 1 femtometer, it will start interacting with the proton. The photon cannot pierce this 1 femtometer without breaking the proton. From the vision of the photon, which is the carrier of the electromagnetic force, so we're looking electromagnetically, it looks as if this photon has like a shell of 1 femtometer. But here comes the ticker. That's for a photon. If we would use quarks or W bosons, for example, to send them at the proton, it is much smaller, because that interaction has a very much shorter range. So then suddenly the proton is not 1 femtometer, but 1, whatever, 10,000 times smaller. So we thinking at that level of sizes, as the 3 quarks are moving around in this marble of 1 femtometer size, is wrong. But I cannot give you a good alternative without making it even more wrong. So have we probed 1 atometer? Well, yes. Does that literally mean we have 1 atometer resolution? Absolutely not. It is more symbolically. We can go to that level of energy state or small things. It means also that if 1 quark, which we believe today is fundamental, would be not fundamental, would be built from other things, like, for example, strings, we will have to go deeper and smaller. But that means the smaller you go, the higher in energy you need to go to be able to pierce that small. So it's more, at that level, let's say, it is more a matter of how high can we go in energy. Is that a satisfying answer?
Yes, unfortunately, this has triggered a lot of other questions, but we don't have to reply. So I invite all our students to send to you these relevant, important questions. Okay, Frederik, thank you once more for this beautiful review. And I give the appointment to our students tomorrow at 3 p.m. So the playlist is the same. And thank you, everybody, and see you tomorrow. Good night.
Bye-bye.